All right, so I guess we are live now. Hi everyone, very good evening to you all, and a belated happy Dashera to you all, everyone out there. So myself, Ayush Tripathi. Currently, I'm working as a problem setter and mentor at GeeksforGeeks, and welcome you all to this post-analysis session of the last weekly contest 176. So kindly let me know if I am audible. Just write a quick plus one as a confirmation from your side so that we can start the discussion. So before starting the contest, I wanted you guys to rate the entire contest on a scale of 10 so that we can improve the upcoming problem set. Improve the upcoming problem set. Just to scale the entire contest on a rate the entire contest on a scale of 10. Just to scale the entire contest and I personally consider this contest as the medium to easy level. All the problems were easy to a moderate level and has lot of learning. So we'll discuss all the four solutions, and I personally found the third problem as more difficult compared to the last one. Okay,
Okay, it is. Is it fine now, Hedwig? Cool. So let's just quickly start with the discussion. And one very important thing, I will discuss all the solution to the point only. So expecting a very high level attention to you guys. And if there is some problem which may not clear to you in this live session, so you can also watch the recording after the session. So this is the first problem which can easily solve with the help of two variables. So Geek String, you are given a string S consisting of a lowercase English letter, that is small a to small z, only 26 letters will be there. And your task is to determine if there exists a subsequence in S such that it is equal to string geek. And here is the definition of the subsequence. That is, it can be derived by deleting some or no elements without changing the order. And we have to return true if such subsequence is present, otherwise false. So let's see how we can solve this problem. So here in this string S, there is a subsequence. Basically, this is a substring, but all the substrings are subsequence. So I will just simply return true. And now let's see how we can solve this problem. So let's say the string which is given to you as A, then G, B, E, let's say then C, E, D, and let's say F and K. And we have to search a we have to search a string. Let's say this is string as a target string. We have to search the subsequence in this string S, which is equal to the target string geek. So what I can do, I can just use a variables, two variables, and I will iterate over all the characters, over all the indices from 0 to n minus 1 in a string S. And what I can do for every index, I can check whether the current index character matches with the character of a target string that we are looking for. So I will use another variable, let's say named as index, and I will initialize this one with 0. So this is basically a greedy problem. Whenever I got a string, whenever I got a character which got match, I will just immediately match the character and increment the value of idx. So here the first index, here in this case, the first character is A, so it does not match with the required character. The required character is G. Then we move to the second index. So let me just write a variable. So this is a variable I, and initially is pointing to 0 and 0 to n minus 1 basically. So the first character not match, then increment the value of I. So here in this case, the value of the next character matches with the required character, which is G. So I will just simply increment the value of idx. That is, take me to the next index and I will match the next index. And basically this is a greedy problem because it is the best time. It is the best time to match the character. Cool. Then take me to the next character, I plus plus, and this is not as required. We want the character E. Then increment the value of I, and it is equal to the required character. So I will immediately match and increment the value of idx. So idx plus plus, take me to the next character. Cool. And then increment the value of I. So I is pointing to character C. I is pointing to character C, not equal to the required character. So take me to the next character. Then the next occurrence of E, and it is equal to the required character. So this is the best time to match. And why we are immediately matching this character E with the current E? Because so that we have more possibilities on the right hand side. So this is a greedy problem. Once you get the character, required character, immediately match it. Cool. And yeah, then I will increment the value of idx. So idx plus plus, it is equal to 3, next index, and then take me to the next character, which is D, not equal to the required character. Then again I will increment the value of I, F, not equal to the required character. Then again increment the value of I, and the next character is key K, which is equal to the required character. So then I will just simply increment the value of idx, and once the value of idx reaches out of the bound, then this simply means you have matched all the characters and return true. So this is the complete solution for the first problem. Let me show you the implementation here. Yeah, this is the solution for the first problem. So this is the method that you have to complete. Given a string str, this is my target string geek, and index in the target string, it is variable idx. Then I iterate over all the characters, and if the current character of the string str matches with the target character, then increment the value of index. And once you reaches out of the bound, that is, you have matched all the character from 0 to target dot length minus 1, then immediately return true. Otherwise, after iterating over all the characters, I will return false. And the time complexity in this case is linear O of n, where n is the length of a string str. So is it clear to everyone? Just write a quick +1 so that we can discuss the next problem. Is it clear to everyone? Yes, no, anything? Cool. So the next problem, which is a palindromic substring. So given a string s and an integer k, and your task is to count the total number of substring of length k in s such that the characters in the substring can be rearranged to form a palindrome. And a string is called as palindrome if it reads the same backward as forward. Cool. So basically you are given an integer k and you have to count the number of subarrays of size k in which the character can be rearranged to form a palindrome. So let's just see what are the properties of the palindrome. So the second problem, palindromic substring. So how we can rearrange the characters and get the palindrome. So let's say this is the string which is given to you, and also you can consider as a substring. It's up to you. So A, B, then C, A, B, and let's say one more occurrence of B and one occurrence of C. So this substring can be rearranged to a palindrome. And how I get this thing? So here you have to check the frequency of all the characters. So the frequency of character A is 2. The frequency of character C is also 2. The frequency of character B, which is 3. So here how I can rearrange this? So just simply map. Here the frequency of A is even, the frequency of C is even. So what we can do, we can just simply divide it by 2 and match it. So A, then C. Now we are left with a odd frequency of B. So we can remove even number, and then we are left with one frequency of B, which I will put here. So this is a rearrange substring, which is a palindrome. So how I get this thing? Just very simple and straightforward approach. Observation, not approach. So if the frequency of all the characters are even, then we can form a palindrome. And if the frequency of at most one character is odd, then also we can form a palindrome. Here you can see we have a frequency of B as odd. So we can form a palindrome. But in case if we have some more than one character which has odd frequency, then we cannot form a palindrome. So let me write approach. So let's say we have a variable odd count. It will simply store the frequency of, it will just simply store the count of characters, or you can say number of characters, which has odd occurrence, or you can say odd frequency. Cool. And if the substring of length k is having this odd count less than or equal to 1, there's a odd count less than or equal to 1, then I will just simply increment my answer. That is, this substring can be rearranged to form a palindrome. So I hope this observation is very much clear to everyone. Now the rest is to apply a sliding window, and not just only this problem, all such problem where you have to iterate over the substring of length k. Just think at least once of a sliding window technique. This is a sliding window problem where the size of the window is fixed. Here the size of the window is k. Window is k. Cool. So let me just draw some random string. So A, B, A, and let's say C, A and A. Yeah, this is the string. And let's say the value of k as 4, or let's say the value of k as 3. So what I can do, I can just first process the first window. I will just simply process the first window, and I will also use a array of size 26 to keep track of the frequency. So array of size 26, where I will map the characters with the indices. So index 0 is for A, then index B is for 1. So index 1 is for B, then index C is for 2, and so on. Index Z is for 25. So once I add the character in the window, I will just increment its frequency in the frequency array, and then I will just simply shift the window to its right. So this is the first window. So this is the first window of size k. So first process the window of size k, and then iterate over the remaining window. So this is the first window. Let me write a pseudocode. So for I is equal to 0 to k minus 1, that is k indices from 0 to k minus 1, and I will just simply increment its frequency. So frequency of s of I minus a. So this is the way to get index from the character, just subtracting the sky value of character a plus plus. Now just simply check. Now just simply check its previous frequency, and if the frequency is odd, then increment the value of odd count. Cool. And then iterate over the remaining substrings of length k. So I is equal to k to n minus 1, n minus 1. And then what I will do, I will just simply remove the contribution of, that is subtract, or I can say, yeah, minus contribution of character s of I minus k. That is okay, let me write in this way, that would much better. So the first step of the window, remove s of I minus kth character from window, and then I will add s of I character in a window. Cool. And then I will find the answer. These are the third step, and these are basically a generic step for all such type of problem where the size of the window is fixed. Then find answer. Find answer. Cool. So this is my first window, first k character, and then I will iterate over all the character from I is equal to k to n minus 1, that is these characters. So this is for the first iteration. And also let me write the indices so that it become more clear to you. 0 1 2 3 4 5 6 7 and 8. So 0 to k minus 1, and then in the next iteration I will just simply iterate from I is equal to k, that is from 3 to 8, and for every character I will remove the contribution of I minus kth character, because we have to shift this window. We have to shift this window. This is the first window, and now I have to shift this window. I have to shift this window by one position. Then again I have to shift this window for each iteration of I. So to shift this window, what I have to do, I have to remove the contribution of the last character and add the contribution of the current character, current index I. So this is the complete approach. Is it clear to everyone? Just write a quick +1 if it is clear to you. What about the other participants? Write a +1. And here is the implementation. This is the method that you have to complete. The string s and the size of the subarray. So then here I am having my answer variable, and then there's a frequency array of size 26, and all the character has frequency 0 initially. Then odd count will simply store the number of character which has odd frequency, and this is for the first window of size k. So I iterate over all the indices from 0 to k minus 1, and this is the current character, incrementing its frequency, and if its frequency is odd, then incrementing the value of odd count, and if its frequency is even, then decrementing the value of odd count, because there might be a case when you have added some character, and after some iteration you got another same character, so the frequency becomes even, so you must have to decrement it once the frequency become even. So after the first k character we have information, and if this odd count is less than or equal to 1, because we can manage only one character with a odd frequency, then incrementing my answer. And then this is the sliding window approach. Every time I will shift this window, so k to n minus 1, then current character which I have to remove. This is the character I minus k which I have to remove, and yeah, removing its decrementing its frequency, and if after decrementing it the frequency is odd, then increment it, otherwise decrement the odd count. Then adding the ith character. This is incoming character s of I, incrementing its frequency, and if the frequency is odd, increment it, otherwise decrement it. Cool. And then here I am finding the answer, updating the answer. If the odd count is less than or equal to 1, then increment the value of answer. Cool. And finally I'm returning this answer. And how much time it will take? So it is of time. This solution is of time complexity linear. We are iterating over all the characters exactly once, 0 to n minus 1. So that's why in this case the time complexity is linear, and the extra space we are using a frequency array of size 26, this one. So that's why extra space complexity is a constant, or you can say O of 26. So now let's just move to the third problem, which I personally found the most interesting problem of the entire contest. Cool. So given an array ARR, and you have to return the count of even length subarray that contain odd number of elements. So there is two things that we have to manage in the valid subarray. The first thing, subarray length must be even, and the number of odd elements must be odd. Cool. So these are the only two conditions that the subarray should satisfy. So let me just discuss with this example, this sample input. So in this array, there are 4 subarrays of even length and with odd number of odd element. So this is the first subarray, 4, 2, 3, 2. It has one odd element, that is odd number of odd element, and its length is even. Then the second subarray, 3, 2. Third subarray, this is the second subarray 2 3, then third subarray 3 2, and then finally there's 2 1. So these are the 4 subarrays which is of even length and are having odd number of odd elements. So this problem can be solved with the help of a contribution technique, and make sure to remember this technique because it is applicable for most of the such problem where you cannot iterate over all the subarrays because of restricted time limit. The value of n can be up to 10 power 5. So you cannot iterate over all the subarrays, otherwise the time complexity would be n square, and that would definitely give you TLE. So in such type of problem we can use a contribution technique. So contribution technique simply says instead of finding the overall answer, find the contribution of each element, or you can say each index. So the contribution technique. So this contribution technique simply says that instead of finding the uh, the overall answer, find the contribution of each index. So my answer is simply equal to I is equal to 1. That is a contribution of each index from 1 to n. Here I have considered one base indexing, and but you can also assume that it is according to zero base indexing. But I will explain with the one base indexing only. So make sure to remember this point. So I will just simply add the contribution of each index. And what is the contribution of each index? It is simply equal to the number of subarrays for a particular index I. Its contribution is number of subarrays of even length, same as the given problem statement, of even length with odd number of odd elements. Cool. And the subarray is ending at index I. Ending at index I. So if I somehow manage to get this information for all the index I, and if I will add them together, that would equal to my final answer. So I hope this thing is clear to everyone. So let's just find the contribution of each index. And after this step, you have to find some kind of a pattern and draw some observation, make some formulas, and solve the contribution. Find the contribution of I, add it in your answer. So let me just draw some array. So let's say the array is named as A, and let's say index 0. I'm not writing its values because this is not our concern. I'm just generalizing everything. So then index 1, index 2, index 3, then index 6. Okay, let me also write index 7. So index 7, index 8, up to index. Instead of saying this as 0, let me just write in terms of one base indexing. So index 1, 2, 3, 4, 5, 6, 7, then index n minus 1, and finally index n. Cool. So this is my array A. And as per my definition of the contribution technique, I want to know the number of subarrays ending at index I, ending at index I, of even length and having number of odd element as odd. So let's say this is a current index I. So this is a current index I. Now please try to pay more attention because this is very very crucial and very much important. So if this is a current index I, what are the subarrays of length of even length? So this is the subarray of length 2, even length, then subarray of length 4, even length, then the subarray of length subarray of length 6, and finally the subarray of length 8. Cool. So let's just use a variable p. This variable p will simply store the parity of index I. So p is equal to I mod 2. Cool. And let's also use another variable. Let's also use another variable q, which will store the parity of odd elements. We'll come to this thing very 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 soon. That's why I'm doing these things. So parity of odd elements, parity of number of odd elements in the subarray from 0 to I. Parity of number of odd elements in a subarray from 0 to I. And how I get this thing? This is simply equal to XOR of all the values from 0 to I and take a AND with 1. So this is equal to XOR of A0, A1, A2, and so on till A of I. And then take a AND with 1. Take a AND with 1. So let me give you an example for this thing. So let's say you have array with the 3 elements, 2, 3, and let's say 5. Cool. So their XOR values, and this is the current index I. I'm assuming this is the current index I. So their XOR value is equal to XOR the binary representation of 2, 0, 0, 1, 0, then the binary representation of 3, 1, 1, then the binary representation of 5, 1, 0, 1. If I take a XOR, then it is 0, 1, 0, and 0. Cool. And if I take a AND with 1, if I take a AND with 1, 0, 0, 0, and 1. So if I take a AND with 1, then it is simply equal to 0, 0, 0, and 0. And this is same as our requirement because here we have a even number of odd element 3 and 2. We have even number of odd element. So that's why the value of q is 0. So just let me know if this thing is clear to everyone. How I get the parity of number of odd element in the subarray from 0 to I. A very straightforward intuition that I am using here. The property of XOR. If the property of XOR 1 XOR 1, which is equal to 0, that is even bits will cancel out each other. Even set bit will cancel out each other, and if there is some odd number of set bit, then the result would be 1. That is 0 XOR 1. It is equal to 1. This is the first observation, first idea that I have used. Take XOR, and then I am taking a AND with 1 because for all the odd numbers, for all odd numbers, LSB is set. So just write a +1 if this thing is clear to you. That how I get the value of q, which is simply equal to XOR of all the elements from 0 to I and take a AND with 1. So if there are even number of odd elements, then LSB is 0, and if there is odd number of odd element, then LSB is 1, and taking AND with 1 will give you the result as 1. Just write a +1. Yes, no, anything. Yes, you can also do the same. Rohit, 0 to I you can also use, also you can take a mod with 2. But this is the idea that I have used to implement the solution. And even your solution is, I guess, more easy to implement. Okay, please, can you please explain it again? Okay, let me just explain it for the last time. So here I have two variables, P, which will simply store the parity of index I, and I just simply get this thing by taking a mod with 2. So if I is even, then value of P is 0. If I is odd, then the value of P is 1. Then the second variable I'm having the parity of number of odd element in the subarray from 0 to I. So to get the parity of number of odd element in this subarray from 0 to I, just simply take XOR of all the elements from 0 to I and take a AND with 1. So let's say in an array you have 3 elements, 2, 3 and 5, and the current index is at the last element 5. So how many odd elements are there? What is the parity of odd elements in the subarray from 0 to I? So to get this thing, take XOR of all the elements. So this is 2, this is 3, and this is 5, and this is the XOR value. And here, if you take a AND with 1, then we are interested with LSB only. And basically, if you take a AND with 1, then LSB is set or not set. There's only two possible cases. So the two values for Q and two unique values for P. Cool. And here I am using this property of XOR. So if there is even number of odd element, then even occurrences will get cancelled out each other. And if there is some odd number of elements, odd elements, then LSB is 1 in this case. Here the LSB is 1 if odd number of odd element. Then I am taking a AND with 1 because we all know for all the odd number LSB is set. The least significant bit is set. So if the result is 1, then it means odd number of odd element. Cool. And once you get this information, then how do I find answer? So let's say from 0 to I, the value of Q is 1. So what does it mean? The value of Q as 1. It simply means, here I am just assuming this sample, this example. You can also test it for 0. So here the value of Q is 1. Then it simply means number of odd elements is odd. Cool. And if the value of Q is 0, then the number of odd elements is even in the subarray from 0 to I. So then what we are looking for? Then we are looking for the indices with the same parity. The indices with the same parity. What are the indices? The index 5. There is the index 5 with the same parity. There is the index 3 with the same parity. That is the same value of P. So at here the value of P. So here the value of P is 1. That is parity of index I. Then parity of index 5. It is also 1. It is odd. So for odd we have 1. Then parity of index 3. It is also 1. Odd. Then the parity of index 1. It is also 1. Cool. And the area starting from immediate next index to I is of even length. So what I'm trying to say, so for all the previous odd indices, the area which starts from immediate next index to I is of even length. So for example, this is of even length, the immediate next index from 5, then immediate next index which is from 4 to 7, this is of even length, then immediate next index from 1 which is 2, that is 2 to 7, this is of even length. So to satisfy the first condition, that is subarray should be of even length, we must have to know the indices with the same parity, and the area which starts from the next index and to index I is of even length. Now the next thing that I want to satisfy is the number of odd elements must be odd. So let's say this index 3, we have this index 3 which satisfy the condition. So how does it satisfy the condition? So we must have the number of odd elements as even. So what I'm trying to say now, please try to pay more attention. So from here, the value of q must be odd. From 0 to 3, the value of q, we must have this as odd. Sorry, even. Cool. Because from 0 to I, we have odd, and from 0 to 3, if we have even, then the area which starts from the next index, immediate next index from 3, which is from 4 to I, is of even length and are having odd number of elements. So here we have odd number of odd element. And how I get this thing? You can just simply easily prove this thing. That is a subtraction of odd and even will also give you odd number. So that is odd minus even will always give you an odd number. So from 0 to I, we have some odd number of odd elements, and from 0 to 3, we have even number of odd element. So the area which is start from 4 to I are of even length and are having odd number of element. So this is the complete solution basically. Now we just have to wrap up and generalize the everything how I will implement the solution. Is it clear to everyone? Yes, no, anything? Just write a quick +1 so that we can discuss how to implement this thing. Cool. And now let's just define DP. So it's very straightforward. Let me repeat it once again. So if the current index is 7, then we are looking for, now please try to pay more attention. We are looking for the number of indices on its left, with the same parity. For example, 5, 6, 5, 3, and 1. These are the indices with the same parity, that is the same value of P. And the number of odd elements up to that index must be of opposite parity. So we are interested to know the number of valid subarray ending at index I. So to get this thing, if the current index is 7, I is equal to 7, then what we want to know number of indices with the same parity, that is the value of P as 1 and parity of number of odd elements as 1 minus q. So this is 1 minus q. So from index 7, The number of subarrays which ends at index 7 is equal to the number of indices on its left with the same parity, and the number of odd elements is even, so that we can get the odd number of elements in a subarray of even length, because we all know if we have odd and if I subtract some even from here, then the result is always odd. This is the basic mathematics property. Cool. So with this idea, we want to have some information from the left hand side. So for this thing, what I will do, I will declare a dp. I will declare a dp array, dp of I current index I mod 2, because we want to know the parity, and the value of q. Here is the definition of q. What is the value of q? So it will just simply store the number of indices so it will just simply store the number of indices in a subarray the number of indices in a subarray from 0 to I with the parity I mod 2 and parity of, that is the value of q, parity of number of odd elements, which is sq. Cool. So how I get this answer? So I will just simply increment my answer, that is answer plus equal to dp of I minus 1, then I mod 2, or you can also say this as a p. So this is I mod 2, or you can also write as p, I mod 2 and 1 minus q. 1 minus q. So this is the value of p. And we all know that if the value of q is 0, then 1 minus q, it is equal to 1. And if the value of q is 1, then the value of if the value of q is 1, then 1 minus q, which is equal to 0. So basically we are just simply changing it from 0 to 1 or 1 to 0. So I will just simply increment my answer by dp of I minus 1, I mod 2 and 1 minus q. Is it clear to everyone? Or is there any other explanation which is required? A very straightforward logic. If the current index is I, then we want to know the number of indices on its left, that is with the same parity. So from this 7, 5, 3 and 1, and the area which starts from immediate next index and 2 index I is of even length. For example, this is of even length. This subarray is of even length. Then the subarray which starts from 4 to 7 is of even length, immediate next index to I. Then the subarray which starts from 2 to 7, that is immediate next index of 1, is of even length. So that's why here we have I mod 2 and then 1 minus q, because here we want to have the parity as opposite of q. So that's why 1 minus q. Cool. Because we all know if we subtract the opposite parity numbers, then we get odd result as odd. That is odd minus even is odd, even minus odd is odd. If you subtract two numbers with the same parity, then the result would be a even number, and if the parities are opposite, then the result would be odd. Is it clear to everyone? Yes, no, anything? So these are the number of subarrays. These are the number of subarrays which ends at index I and having even length and odd number of odd elements. Cool. And then how I will update this dp of I mod 2 and q. So this is very straightforward. dp of I, then I mod 2 and q, which is equal to dp of I minus 1 from 0 to I minus 1. Then I mod 2. How many indices in this subarray from 0 to I minus 1 with the parity I mod 2 and the value of q and plus 1 because we got one more index. Cool. And first I will update the answer, and then I will increment the value of dp of basically first I will increment the find the answer and then I will update this thing. But there is one property which is optimization of memory in a dynamic programming. But before this thing, let me just discuss a base case. So what would be a base case here in here? So dp of 0, that is subarray of length 0. There is also a subarray of length 0. Cool. And in a subarray of length 0, the parity of odd elements. The parity of first we have I mod 2. So here it is also 0. And the parity of odd elements, that is no odd element in a subarray of length 0. So that is 0 number of odd element, and 0 means even, and even means 0. Basically the value of q as 0. It is equal to 1. In a subarray of length 0, we have 0 odd element. So this is the base case we have. So that's why I have implemented according to one base indexing. But in case if you are writing a top-down approach, that is recursion plus memorization, then you don't have to assume a one base indexing. But since I have to declare one index for a empty subarray, that's why I'm using one base indexing. Cool. And another thing, another optimization, which is a space optimization. If you have noticed here, then for every index I, for the current index I, what I am accessing? I am accessing just a previous value. Previous value, that is index I minus 1. So for this thing, we can omit this one dimension. You are just only accessing the previous one. So this problem, this 3D dynamic programming problem, can we reduce it to 2D dynamic programming? And from here and from here also. Just move in a progressive order and declare a variable, declare an array of size 2 cross 2 because there are only two possible values for p and two possible values for q, and store the information in a progressive order for the current index I. First update the answer, then update the dp array, and then take me to the next index. And here is the base case, that is a dp of 0, subarray of 0, subarray of length 0 has 0 number of odd elements, so it is equal to 1. Cool. So let me just show you the implementation. And yeah, here is the implementation. So here is my answer, that is the result which I have initialized with 0, then a dp array all initialized with 0, then this is a base case, and here we have a variable pre, that this is to compute the value of q, that is XOR of all the elements and take a AND with 1. Cool. So I'm updating, that is taking XOR with ARR of I. So the previous XOR from 0 to I minus 1 and XOR with the current element. Then this is the value of P, that is parity of index I. So I plus 1 mod 2. So here I have used one base indexing, and the value of Q is simply equal to prefix XOR and 1. Cool. And then I'm updating the answer, that is number of indices in its left. And since we are moving in progressive order, so we have the information up till 0 to I minus 1 only. Cool. So the number of indices in from 0 to I minus 1 and with the parity P, and the parity of number of odd elements as opposite 1 minus q. Cool. And then I'm just simply incrementing the value of dp of p and q. So I hope this thing is clear to everyone. Cool. And finally, I'm returning this answer. The time complexity is linear. The extra space, which is this array of size 2 cross 2, so which is constant, can be considered as constant. So the time complexity is linear and the space complexity is constant. Is it clear to everyone? Just write a +1 if this thing is clear to you. Write a +1 so that we can quickly move to the next problem. Yes, no, anything? Just write a quick +1. Cool. So let's just quickly solve the final problem of the contest. And I personally found this one as easiest as compared to the last one. So subarray occurrences. So you are given an array of length n, and you are provided provided with the q queries, and in each query of the form three integers l, r, and k, and you have to count the number of occurrences of integer k in the subarray from l to r. Cool. And you should return the answer for each query individually. So this is very obvious thing. So the overall problem statement, given an array of size n and q queries, in each query you will be given three integers l, r, and k. You have to find the number of occurrences in the subarray which starts from index l to r. So let me explain you with this example. So the first query, and basically here the query is also given in terms of zero base indexes. You can check the constraint here. The value of L starts from 0 to less than n minus 1 up to, and the value of k can be up to 10 power 9. So the first query, index 1 to 4, and you have to find the number of occurrences of this 2. So here we have 3 occurrences of 2. So the answer for the first query is 3. Then the second query, which starts from index 0 to 6. So the entire array, I guess. Yeah, entire array 0 to n minus 1. And here we have the number of occurrences, how many occurrences of 1, which is 2. So this is the first occurrence of 1, then the second occurrence of 1. So I hope the problem statement is clear to everyone. Now how we can solve this problem? So to solve this problem, let's just analyze the constraint. Square root decomposition giving for the last question. Okay, given clearly for the last question. Okay, so basically you don't have to use a square root decomposition. I admit that the queries are offline queries are there, but this problem can be easily solved with the help of binary search and some map container, and in Java it is a tree map. But the queries are offline, so you can also solve it using a square root decomposition. Cool. Anyway, so the number of elements, that is n, can be up to 10 power 5. Can be up to 10 power 5. Then what does it mean? It simply means only at most 10 power 5 unique elements will be there in the array. Only at most 10 power 5 unique elements will be there in the array. So to solve this thing, what I can do, I can use a map. When you have a discrete data, in case if you are having a continuous data, that is if all the elements are from 0 to 10 power 5, 0 to n, then you can use array. But in case if you do not have a continuous data, that is a discrete data, then we must have to use a map or unordered map. So I will use a map, and basically a nested map of map in C++. In case if you are using Java, then it is a tree map. You cannot use a hash map or unordered map in C++ because the unordered containers are not defined for the complex data type. So yeah, map. So then map of map. So here the key is map, key is integer, and each value is a map in itself. So this is a nested map, let's say MP, and here this MP will simply store MP of x comma I will store the number of occurrences of element x in the subarray from 0 to I. So this will simply store the frequency of element x in the subarray from 0 to I. So do not get confused with this thing. So MP of x will simply give you the map which is corresponding to key x, and with the help of this second key, you can access the value of a map. Cool. Then how I will update this thing? A very straightforward thing. So for I is equal to 0 to n minus 1, MP of a of I and I, that is the number of occurrences, that is a frequency of element a of I, it is simply equal to the previous frequency of a of I plus 1. So MP of a of I dot size, that is what is its size, and plus 1. So let me just try run for some particular example. So let's say you have elements, and what I can say here. So let's say I'm not going to write rest of the elements. I'm just only I will explain with that by taking one element as a reference. So let's say the element 5, then element some more elements are there, then another occurrence of 5, then another occurrence of 5, let's say, and then some more elements, and then again element 5. Cool. So how I will update my map? So initially MP of 5, that is what we can say, yeah, initially this MP of 5, that is frequency of element x is 0, so that's why it is of size 0. And then let me also write the indexes here. So index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Cool. So initially its size is empty. Then at index 2 we got 5. So what I will do, I will just simply add the key value pair, the previous size which was 0 and 0 plus 1 which is 1, and index I. So what I'm trying to say, the number of occurrences of 5 from 0 to index 2 is 1. Cool. That is I will add this key value pair. Then this is the first occurrence of 5. Then the second occurrence of 5 is at index 6. So the previous size of MP of 5 which is 1, and 1 plus 1 which is 2, as we got another occurrence. So I will add a key value pair which is what we can say, yes, it is 6 comma 2. Cool. So at here we have MP of 5 and 2 as 1. Then at here we have MP of 5 comma 6 as 2, and at index 7 we have MP of 5 and 7, that is the number of occurrences from 0 to previous occurrences plus 1. So it is 2 plus 1 which is equal to 3. So I will add a key value pair in map of 5 which is 7 comma what we can say 3. Yeah, 7 comma 3, previous size plus 1. And finally For index 11, it is MP of 5 and index 11, which is equal to previous size, which is 3 plus 1, which is equal to 4. So I will add a key value pair 11 comma 4. Cool. So do not get confused with this definition. MP of I comma x will simply store the frequency of element x in the subarray from 0 to I. And then how I will find the answer. So let's say this is the query which you have to solve. Start from index 1, that is the value of L as 1 and the value of R. Let's say the value of R as 6. So this is the query that you have to answer. This is the query that you have to answer. From 0 to 6, you have to count the number of occurrences of 5. So how to get this thing? So to get this thing, this can be easily solved with a binary search. So value of k as 5. So first what I will do, I will find the upper bound of this R. So this is index R. This is L. And this is index R. So first I will find the upper bound of this R to get to the immediate next index. So first I will find this upper bound of R, but with the upper bound function. So upper bound of R, and then what I will do, I will find this lower bound of L. Lower bound of L. So the lower bound of L, that is the lower bound key, which is 2. So this is the lower bound of L. Lower bound of L. And the upper bound of R, here the value of R is 6, so its upper bound is 7. So this is the upper bound of R. So upper bound of R. Cool. Upper bound of R. And now I can just easily compute the number occurrences of K in this range from L to upper bound minus 1. So this is upper bound index 7, and this index 2 is the lower bound. This index 2 is the lower bound. So my answer is simply equal to MP of, let me write here. So my answer is simply equal to MP of K and then upper bound minus 1. Upper bound minus 1. So that I can easily get to the index 6. So that I can easily get to this index. And that's why I have taken upper bound, just to be on the safer side in all the cases. If you are taking the lower bound, then it will give you index 6. And if you subtract 1 from here, then you will get the wrong result. But in case if you are taking the upper bound, then you can always subtract 1 from here. Upper bound will give you the smallest number which is greater than the required, the R, the value of R. The smallest key which is greater than R, which is greater than R. Cool, because there might be a case when R is not present in this map. So in that case, upper bound and lower bound will give you, upper bound and lower bound will give you the same result. Cool. So yeah, MP of K upper bound minus 1 and then minus MP of K comma L. Cool. And then plus 1. And why this plus 1? Because here it will give you the occurrences of 5 in this area from L plus 1 to upper bound minus 1 in this area. And we have to add plus 1 because this L is also inclusive. So that's why plus 1 for this. As it is mentioned in the problem statement, L and R both are inclusive. So that's why this is the formula we can use. So I hope it is clear to everyone. And yeah, this is the complete solution. Let me just discuss the implementation here. So here, this is the method that you have to complete. And here I am having my 2D map. Then updating this map, MP of x comma I is simply equal to the previous size plus 1. Then here I am having answer vector of size q, initializing all the elements with 0. That is frequency of k as 0. And this is the index for answer array, this index A. And this is for the queries part. Cool. So while q minus minus, this is simply iterating over all the queries, and lr and k, these are the values of lr and k. Then take me to the next query for the next iteration. Then this is the current map. So mp of k, this is the current map. And just for an explanation purpose, I have taken the nested map as a reference. You can also use the same nested map. Cool. And this is the lower bound, and it return you iterator. That's why here I'm having auto keyword. Otherwise, you can also declare iterator variable. And then here I'm having upper bound of r. Then I'm checking if upper bound and lower bound both are same. Then it means no occurrences of k is in the subarray from l to r, because both are pointing to the same index. So in that case, my answer will be 0. And then I will just simply continue. Otherwise, upper bound minus minus, that is floor it minus minus, and this will be my answer. Here I am accessing the value with the pointers with the help of iterator, and you can use arrow for this. Otherwise, you can also write in this way, that is mp of k comma upper bound and lower bound, as same as that we have discussed. Cool. And then plus one, because l is also inclusive. So yeah, this is the complete solution. And how much time it will take? So this will take n log of n base 2. And then we are answering the queries in a time complexity q log of n multiplied by log of n base 2. So the time complexity here in this case, it is n log of n base 2, as we have a nested map. Then answering the queries, iterating over all the queries, and then checking in map the values. So log of n multiplied by log of n base 2. This is the time complexity. So this is the complete solution for all the 4 problems. And if there is some problem, there is something which is not clear to you, so you can watch the recording of the session. So now we are good to wrap the session. In case if you are having any query, then just go with your queries. I will answer all your doubts. Otherwise, just let me know so that I can wrap the session. And make sure to hit the subscribe button, and also write your comment. Also write your feedback in the comment section. That would help me to improve more upcoming sessions. Cool. So I guess no doubt so far. We are good to wrap the session. So thank you so much, guys, for watching this stream, and have a good day. Laksh, you can share your square root decomposition solution in the comment. If I get the time, then I will evaluate and find the mistakes. But the square root function is bigger than the logarithmic functions. So maybe that's the reason why you are getting a TLE. Cool. So thank you everyone, and have a good day.